Hello, MRC. This video is an introduction to zero forcing as a graph coloring process. In the earlier videos, you've heard about several applications of zero forcing, some of which are listed on this slide. That is not the focus of this video, though. Zero forcing is a coloring process where blue vertices are able to color white vertices, but only some blue vertices are allowed to color only some white vertices. And which blue vertices are allowed to color which white vertices is determined by a color change rule. That color change rule says that a blue vertex can perform a force on a white vertex. In other words, the blue vertex can turn the white vertex blue if the white vertex is the only white neighbor of the blue vertex. For example, consider the graph at the top of the slide, which consists of two disjoint paths. We can start with a set of initial blue vertices. In this case, I've chosen a single endpoint from each path. And then we can iterate the color change rule until no more white vertices can be colored. What does this mean? Well, we see that this vertex becomes blue right here, and same with this one. Now this one that just turned blue can color this one, and same over here on the right. And so on and so forth. The whole graph is able to turn blue. Now, note that if a blue vertex colors some white neighbor in some step of this coloring process, then that blue vertex will never be able to color any more white vertices for the rest of the process. That's because if that blue vertex only had a single white neighbor at an earlier step and it turned that neighbor blue, then at all later steps, that blue vertex has all blue neighbors. Another thing to note is that in some rounds, there might be multiple blue vertices that are able to color their white neighbors. For example, the graph at the top of the slide, we see that at the first step of the process, we had multiple blue vertices that were able to color their white neighbors. So we can think of this in multiple ways. We could do all possible forces in each round in parallel, or we can require only one force per round. If we choose the latter, there could be different ways to order the forces in rounds where we have multiple blue vertices that have single white neighbors. Again, an example is the graph at the top of the slide. We could have chosen the order of our forces to be the right blue vertex coloring its neighbor first instead of the left blue vertex, or we could have started with the left one and done the right one. Either way would have been fine. Now, regardless of what order we choose, the final coloring of the graph that we obtain will be unique for any initial set of blue vertices. So it's fine for us to think of the forces happening in parallel, where in every round of the coloring process, every blue vertex with a single white neighbor will turn that white neighbor blue. And this is the way that we'll think about propagation time when we get to that later in the MRC, but we're not going to cover that in this video. So a natural question to ask is, given some graph, for what initial sets of blue vertices can we eventually color the whole graph blue using the zero forcing coloring process? Just like the graph that we saw at the top of the last slide. Now, this graph that we have right here, a cycle, currently I've drawn two blue vertices, and we see that if we try to iterate the color change rule on this graph, nothing will ever get colored besides these two vertices, because each of these two blue vertices has two white neighbors. Now, if my initial set of blue vertices had an extra blue vertex, so here's an extra one. So now I've modified the initial set. I have three adjacent vertices. Now we see the color change rule can be used to color this whole cycle. So if we're given a graph G, we call a subset of its vertices a zero forcing set if the whole graph can be eventually colored blue by iterating the zero forcing color change rule, starting with just the vertices of B blue. For example, for a path, a zero forcing set would just be an endpoint. There will also be many other zero forcing sets of this path, but if we want the smallest zero forcing set, we're going to have to choose an endpoint, either this one on the right or that one on the left. Notice that if we chose an interior point of the path and we only have one vertex in the zero forcing set, that's not going to be a zero forcing set because that interior vertex has two white neighbors. A minimum zero forcing set is just a zero forcing set of minimum size. For example, with the path, we can take one of the endpoints and we see that this can be used to color the whole graph. For the cycle, if we try to only use a single initial blue vertex, then we'll run into a problem that vertex has two white neighbors. So no other vertices will ever be colored in this graph. So we need more than one initial blue vertex for a cycle. We need at least two. And we see that two works by placing them adjacent to each other, and then the whole cycle is colored blue. We can also look at complete graphs, and we see with complete graphs that we have to color all but one vertex. And that's because if we color fewer than n-1 of the vertices for a complete graph of order n, then we're going to have at least two white vertices, and those two white vertices are neighbors with all the other vertices. So all of the blue vertices will always have two white neighbors. None of them will ever be able to perform a force. For a star, similarly, if we color fewer than n-1 of the leaves of a star that has n total leaves, then we'll have at least two white leaves. The only vertex of a star that can color the leaves is the center vertex, and that center vertex will always have at least two white neighbors, so it'll never be able to color those two white leaves. The zero forcing number of a graph is defined just in terms of the minimum zero forcing sets as their size. For example, the path, we saw the minimum zero forcing sets were the endpoints, so the zero forcing number is 1. For the cycle, the zero forcing number is 2, because the minimum zero forcing sets have size 2, and they are adjacent pairs of vertices. For the complete graph of order n, the zero forcing number is n-1, any subset of size n-1, and for the star with n leaves, the zero forcing number is n minus 1, and our zero forcing sets are any subset of n minus 1 leaves. So let's discuss several basic facts about the zero forcing number. First fact, if we have a graph with multiple connected components, then the zero forcing process in one component has no effect on the zero forcing process in another component. So the zero forcing number of the whole graph is just the sum of the zero forcing numbers of each of the components. Here's a simple inequality for the zero forcing number. The minimum degree of the graph is less than or equal to the zero forcing number is less than or equal to the order of the graph. For the right side of the inequality, we can see that just by coloring every vertex blue initially, and then the process is already finished. For the left side, we can consider the first vertex to perform a force in the zero forcing coloring process. That vertex must have all of its neighbors blue except for one. So the total number of blue vertices initially must be at least 1 for that vertex plus its degree minus 1, which is the same as the degree of that vertex, which is at least the minimum degree of the graph. Here's another inequality for a slightly more specific family of graphs. If G contains at least one edge and G has order n, then the zero forcing number of G is at most n minus 1. How can we see this? Well, let's take that edge, and let's suppose that edge is on vertices U and V. Let's color all of the vertices of G except for V. Then V is going to get colored on the first step. So we just exhibited a zero forcing set of size at most n minus 1. Now, what happens if the zero forcing number is 1? So we already saw that the path has a zero forcing number of 1. But let's say that we have some graph that has zero forcing number of 1. So it starts with some initial blue vertex, and only one initial blue vertex. Now, if that's the only vertex of the graph, then we have a path of order 1. If there are any other vertices in the graph, then this initial blue vertex must have some neighbor. It must have a white neighbor. And since there's no other blue vertices in the graph, that white neighbor must be its only neighbor. So in the first turn of the process, this initial blue vertex will color its white neighbor blue. Now, if these are the only two vertices in the graph, then we have a path of order 2. Otherwise, this vertex right here on the right must have some white neighbor, and that white neighbor must be its only neighbor. And now we got a path of length 3. And we can just keep on doing this process, and we always get a path, regardless of the order of the graph. Now, what happens if the zero forcing number is n? Well, we can actually see right away that if the zero forcing number is n, then our graph cannot contain any edge. So that tells us that the graph has to consist of all isolated vertices. On the other hand, if the graph consists of all isolated vertices, then we see that the zero forcing number is just the order of the graph. More specifically, we can consider connected graphs of order at least 2. And we can say that for these graphs, the zero forcing number is n minus 1 if and only if the graph is complete. So we already saw that the zero forcing number of the complete graph of order n is n minus 1. On the other hand, we can suppose that we have a graph of order n that is not complete. This means that there are two vertices in the graph, u and v, and there's not an edge between them. So consider the initial set of blue vertices where we color every vertex in the graph except for u and v. Since the graph is connected, u and v are both going to get colored on the first step of the coloring process. So we just exhibited a zero forcing set of size at most n-2, which means that the zero forcing number is not n-1. One of the most useful tools for thinking about zero forcing sets and the zero forcing number is zero forcing chains. So if we start with some zero forcing set, like the one we have for this graph with these two blue vertices, we can construct disjoint chains, one chain for each initial blue vertex. And the chains, I'll draw them here. They just consist of the vertices that force each other in order. So this graph has exactly two chains, and these chains are the two paths in the graph. If our graph was just a single path, then it would only have a single zero forcing chain if we started with a minimum zero forcing set. So if we started, for example, with this vertex blue, this would give us just this single zero forcing chain. On the other hand, say we started with this vertex and this vertex blue, then we can have a zero forcing chain over here and a zero forcing chain over here. Similarly, we can do zero forcing chains for a cycle. So we could take two adjacent vertices and do some zero forcing chains for them. But note that there's often multiple ways for us to choose the zero forcing chains if we don't assume that the forcing is happening in parallel. So, for example, the one we just drew here, we could have drawn something like this. Another one we could consider, suppose we have some graph over here. The triangle. And we have these two initial blue vertices. Now, even if we are performing the forces in parallel, we can make a choice of which of those blue vertices gets to force this last vertex here. So that vertex can be part of either of these zero forcing chains. Now, an immediate inequality that we get from zero forcing chains is the fact that the path cover number of a graph is at most its zero forcing number. And this follows because the zero forcing chains are a path cover of the graph. Another useful tool for zero forcing sets is called neighbor trading. Suppose we have some zero forcing set, Z, and we have some vertex U and Z, which has degree at least 2, and U has only a single white neighbor named W. Then we can construct another zero forcing set by switching out V and putting in W. In other words, the zero forcing set is Z union the singleton W minus the singleton V. For example, on a cycle, we have this zero forcing set right here. We can take this as our vertex U, and we see that U only has a single white neighbor over here. I'll name that W. And the other neighbor is V. So our new zero forcing set is this one right here. Another useful tool is the reversal. So we can start with a zero forcing set, Z, with K elements, V1 up to Vk. We can draw any set of zero forcing chains for Z, and we can let W1 up to Wk be the ends of the chains that are opposite from V1 up to Vk. Then the set of the Wi's, I equals 1 to K, that's the reversal of Z, and it's also a zero forcing set of the graph. Now, I just want to emphasize, for the reversal, we have to take the opposite ends of all the chains. We can't just take opposite ends of some of the chains. So for example, we can consider a cycle. With a cycle, we start with a zero forcing set. We pick some zero forcing chains for it. And the endpoints of those chains, that gives us the reversal. And note that there will be multiple choices of the reversal for this cycle here, because there's multiple ways to choose the zero forcing chains. And right here, this reversal is a zero forcing set. However, if I only chose an opposite end of one of the chains, so say I chose, I'll put them in boxes, this one here and this one here. So I chose one of the initial ones we started with, and then I chose one of the opposite ones instead of both opposite ones. We can see that that's not a zero forcing set. So we really do need to use all of the opposite ends, not just some of them. Here are a few other basic facts about zero forcing. So if we have a connected graph G of order greater than 1, then no vertex is going to be in every minimum zero forcing set of the graph. So if you think about all the families of graphs that we saw so far, all of them were connected and had order greater than 1, and every vertex in those graphs was excluded from some minimum zero forcing set. Another basic fact is that the zero forcing number is 2 if and only if the graph is on 2 parallel paths. What does it mean to be on 2 parallel paths? It means that the path cover number is 2, and we can draw the graph in the plane so that the paths are parallel line segments, and the edges between the paths do not cross each other, and the edges are straight. And I've drawn several graphs on 2 parallel paths at the bottom of this slide. You can see that all the edges between paths are straight. You can see that some of these paths only have a single vertex. All of these graphs will have zero forcing number of 2. And that brings us to the end of this video. Thanks for watching. If you have any questions, please feel free to email me.